Now members, we are going to see a case when we have a string like this, when it's a concrete string, and then we attach a particle in mid or somewhere there on it. Then as this one is moving, so that we are going to be having in this case. So this is the case we are going to consider as this string is moving like that. So that's what we are going to have in this example. So a light out string AB of length 2,700 meters has a particle of 4 kilogram mass attached to it at speed 170 from A. 170 meters from A. The end of the string attached to two fixed points in the same vertical line with A 210 meters above B. The particle moves in a horizontal circle 150 meters vertically below A and at a constant speed of 20√3 meters per second. Find the tension in the two parts of the string. Okay, in our solution, they are giving us mass as 4 kilograms. They are giving us the velocity as 20√3 meters per second. What else? Okay. So now they are telling us that we have two ends of the string. So our string is, first of all, this would have been the case. So this is the string here. It's fixed, two ends of the string are fixed. Then as this one starts moving, I think you can see it's going to be forming. I think this is how the strings are going to be. They are going to be in that, I want it to be in that form. I think this is where the strings are going to be. So when they are here, this one is going to be pulling it then towards the side as it's moving. So two ends are attached, so vertical above A. So this is, vertical above B. So they are telling us that this is going to be, if this is our A, they are telling us that A 200 meters above B. So this is going to be our B. So let me try to. So this is going to be our B. Let me try to reduce on it so that it's not too long. So let me say that is going to be my B. But from here up to here, we have 200 meters. Okay. Now they are telling us that now a string AB. This AB now, when they are this one, when they put it to this side, this particle is going to be pulling it in this order. It's going to pull it one side, that side. Then as it's moving, it's going to be forming a circle. That's going to be its radius. Then this end will be coming to this part there, B. So they're telling us that this is now our particle. Of course, we are going to be having weight here. The weight is going to be now the mass times gravity. There is no contact, so we don't have reaction. So they're telling us that this is 2,700 meters. A particle attached to it at P. So this is our point P now. At P, 170. So this is 170 meters from 170 meters from A. The ends of the string are fixed with 110 meters above that, so that's okay. Okay, now if this is this is supposed to be 270. This is 270, not 2. This is 270. So if that's 270, it means, but they're telling us that from here up to here is 170. It means that now the balance is going to be 100 meters, like that. So if we have that as the case, they're telling us that now, the particle moves in a horizontal circle 150 meters vertically below A. So this is A. This is A. So 150 meters below A. Of course, we are going to be having the circle which this one is moving. Remember, this one is moving in the circle. So now, From here up to here, they are telling us that now it's 100 and it's 150. But remember that from here up to here is 210. So meaning the bars from here up to here, we get 210 minus this, we shall be getting 60 meters in that order. Okay. Now from there, we are going to be having now, I think we can see we can get the radius. This radius here, from here up to here is going to be our R. So using this triangle here, we can ably get our R. If I do it this side, I think you see this is 170, this is 150, then you can get to this. So that's going to be, we get 170. So this one is going to be 80 meters. So these are meters using Pythagoras. So this radius is going to be 80 meters. So that's the case we have. Okay, this one is going to be at an angle we are going to call theta. And then this one is going to be at an angle I can call alpha. So basically, that's what we have so far. Now, the idea is, now, we are going to be having different tensions in this string. Remember, this one is going to be pulled towards there. So this one we are going to be having tension in that string. They are going to be different because the lengths are also different. This one. So also here we are going to be having a different tension 2. This one is going to be pulling this part towards this, and this one is going to be pulling it towards that. So now meaning, if you are trying to resolve basing on theta, if I try to resolve this one, upwards here, basing on the theta, this one is going to be T1, this is adjacent, cos theta, and then upwards, because this force is moving like that, so I'm moving and then up. This one is going to be T1, then sine theta, because this one is opposite. Okay, well now based on alpha, this is going to be adjacent, so it's going to be now, this is now the tension, T2, now cos alpha, then it's going to come and also going to move like that, which is going to be T2 sine alpha. So those are the cases we have there because this is opposite to that. All forces we want here, they should be in either horizontal or vertical way. We don't want anything like slanting. This one is not one, that's why you resolve them. So from there, now let me say resolving upwards, you see we have T1 sine theta, then I think we see a subtracting, this one is going down, T2 is sine alpha, that one is going to be giving us upwards, so this is the force acting upwards. I think we see this one minus that one, it's going to be equal to this one, which is of B. Or you can say this one is equal to this plus this. It's up to you. So now here you know what we can get sine alpha. If I'm here, I can remember this is going to be my theta. So from there I see that my sine theta is going to be the opposite over hypotenuse. So cos theta is going to be adjacent over hypotenuse. Now, I can also draw for this one, of course, alpha. So this is our alpha, this is 80, this is 60, then this is 100. So now you can start there, our cos, our sine alpha is equal to the opposite over hypotenuse, then our cos alpha is adjacent over hypotenuse. So those are the cases we have. So when I put them here, so I have T1 into now sine alpha, you see that we can reduce these ones. So we have 15 over 17, then minus T2 into sine alpha, which is 6 over 10, equaling to 4 times 9.8. So you can see, I can illustrate also it's going to be 170. So this will multiply here and this will multiply here. So when I get this 10 times here, I will have 150 to 1, then minus 6 times 17, be 102 to 2 equaling 2. Now 4 times, then times the LCM, which is 170. And there shall be adding 6, 6, 6, 4. So I call this one equation 1. Okay, the other part is we are going now to resolve horizontally in this order. But remember, we said all horizontal forces should be equal in 2. That's the centripetal force. To resolve in that way, so now we are going to be having, first of all, this T1 cos theta. You still also have this one going in that direction, then plus T2 sine alpha equaling 2. Now this one has to be equal to m v squared over r. This one is the force. We said in horizontal, these horizontal motions, any force vertical should be equal to the centripetal force as is there. So here we have T1 into our cos theta. You can see it's going to be 8 over 10. If we reduce, we can reduce 10. Okay, then plus T2 sine alpha. Okay, sorry, I was on cos theta. So cos theta is here. 8 over 17, over 17. Then T2 is going to be sine alpha, which is 6 over 10. 6 over 10 equaling to our mass, which is 4 times the velocity, which we are going to be having as 20, root 3 squared, then the whole over the radius from here up here, which is 80. And so from there, I think you can see we are going to be having 8t. So this is going to be this times this. We are going to be having 80 t1. 80 t1. When I get this times this, then I get 17 times 6, which is going to give me. Sorry. 17, where did I get this sine alpha? Then this one, sine alpha. Sorry, this is going to be cos, not sine. This is cos alpha. Sorry for that. Error. So this one is supposed to be cos alpha, not sine alpha. This is cos alpha. This force here, cos alpha. And from there, see our cos alpha is going to be 8 over 10. Yeah, cos alpha is 8 over 10. This one here. This one is not sine, it's because we are adding this and this. Okay. So then from there, when you simplify, this one is going to be 8 to 1. Then we have 8 times 17, which will be plus 162 equaling 2. Now here we have 4 times 23 squared divided by 80. Then times 170. So here we have 10,200. I call this equation 2. So equation 2. And then you can easily solve. So solving 1. So you see, solve 1 and 2. So I think everyone can solve two simultaneous equations. Let me pause and then I get the answers there. Okay, now what we do, put them here. Now after that, from 1, I can make this the subject 1. I take this beside and I divide by 150. So then after this, now I have 2, 1. Now I put this 2, 1 in here. When I put it here, then we simplify. Our T2 there is going to be, my T2 is going to be, 3, 4.9048 newtons. Then when I come and I put this here, so from 3, you can start 91. It's going to be now 6664, then plus 10, 2 into now T2, which is 34.9048, the whole over 150. So my T1 is going to be, 68.1619 newtons, and that's going to be my answer. So basically, that's how we had to attempt that question there. When we have that resolve vertically, resolve horizontally, this is horizontal, this is horizontal, they are equal to the centripetal. Vertically, when we get this, is equal to this plus this. Simple. So, well, that's it, members. I wish you well. Then solving simultaneous equations, I think that one everyone can do. Then we have that. So, that's it. Wish you well.